All right, now we're in 4.3 and we are graphing proportional relationships. So our goal here is to graph proportional relationships and understand direct variation. So these might be foreign terms to you a little bit, but that should be the title at the top of your page to get us started. So I should see 4.3 graphing proportional relationships at the top of everyone's notes. So first, let's look at what we know, proportional. What have we done with proportions? Or what do we think about when something's proportional? Well, we have solved proportions such as x over 3 equals 5 over 15, right? And then you can just cross multiply here. So you get 15x equals 15, divide by 15, divide by 15, x equals 1, right? So we solved this proportion because this is saying if we plugged it back in to x here, that 1 over 3 equals 5 over 15, that those two fractions are proportional. And are they? Yes, because 5/15 simplifies to 1/3. So yes, these are proportional fractions. So we're just going to use this knowledge of what a proportion is, meaning like 5, to go from 5 to 1, what did I divide by? Divided by 5, right? And to go from 15 to 3, I divided by 5. Likewise, if I was going from 1 to 5, I multiplied by 5, and if I was going from 3 to 15, I multiplied by 5, right? So they're changing by the same rate, right? The same constant of proportionality. That is a big key word, so let's look at it. The constant of proportionality, it's that number that both the numerator and the denominator in the fraction are multiplied by to get an equivalent fraction or a proportional fraction, right? So, but we're talking about linear equations now, right? So think about it. If I have y equals mx plus b, in this equation, where might the constant of proportionality be? Remember, we multiplied to get equivalent fractions in our proportion. So where would the constant proportionality be probably in this equation? Is b being multiplied by anything? No, so we can take that out, right, in the addition sign. What about, could it be x? Well, no, because x and y are like they're a pair, right? They're a coordinate pair. So that leaves us with m, right? And what is m in this the equation y equals mx plus b, which is, again, slope-intercept form? What is m's function? What does it represent? Slope, right? So the constant of proportionality is the slope of a line in this form. Y equals mx, no b. So what is b then? If there's no b written in this case, what is it? What is the value of b? 0, right? So b equals 0 in this case. Meaning, if you have a graph, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, every line in this form is going to go through which point on this graph, knowing that b equals 0? Well, again, b is the y-intercept, right, which is where the line crosses the x-axis. So if b equals 0, it means it intersects this line right at the origin, right? It's 0, 0. So every single line in this form is going to pass through the origin, through 0, 0, because b equals 0. There's no b out here, right? There's no b. It's 0. So let's look at this y equals mx a little bit more closely. So in this case, m is my constant of proportionality, okay? And because I only have m, that is the only thing that x is being multiplied by and y is not being multiplied by anything, x and y are considered to be in direct variation of one another because their only difference is m, right? Their only y is equal to x times m. So you could say that y is 3 times x, right? So nothing else is being added into this equation except m is making them vary between each other. And that's the direct variation because it's only m. So for your notes, definitely have m is the constant of proportionality, and please write out proportionality, I just don't have room here. Constant of proportionality, and this equation is direct variation. So anytime you think about something varying directly, or you see in a problem the words direct variation varies directly with, know that this is the equation you're dealing with. So let's look at an example. So here we have the weight y of an object on Titan, one of Saturn's moons, is proportional to the weight x of the object on Earth. So we're talking about weight. We know they're proportional. An object that weighs 105 pounds on Earth would weigh 15 pounds on Titan. So let's write an equation that represents this situation. So we have the numbers 105 and 15, right? So we can just make that a point, 105, 15. But it's important to know that, okay, 100, if this is our x and this is our y, x represents the weight on Earth, right? And y represents the weight on Titan. So those are important things to note so that when you draw your graph, you know that the x-axis is Earth weight and the y-axis is Titan weight, right? But we're not worried about the graph yet. So we're just going to use our equation y equals mx. We can plug in 15 for y. M we don't know. Our constant of proportionality, we don't know yet. If it's this much on Earth, what do I multiply or divide it by to get the weight on Titan? I just know the two different weights, and I know that they're proportional. So we're going to solve for the constant of proportionality. So m times 105, divide by 105, divide by 105, and I get 1/7 equals m. So the equation then, using this information, my slope is 1/7, right? I have y equals 1/7 x. And is that in equation form? Is that acceptable? Can we graph that? Yes, absolutely. Because this is, again, this is like slope-intercept form, y equals mx plus b. We just don't have the b in here. The b is 0. So we can start at 0, and if we have, this is going to be a rough graph, but say this was 5, 10, 15, 20, and 1, 2, 3, 4. Up 1 over about 7, right? Up 1 over about 7. So our graph is going to look something like this. And that's the graph of y equals 1/7 x. So we used the information given to solve for m using this direct variation equation. And then we plugged m back in to this equation to get the equation of our line to represent this situation of the weights on Earth and the proportional weights on Titan. So given that the equation representing the relationship between those two weights is y equals 1/7 x, if I wanted to know now how much would a chunk of ice that weighs 3.5 pounds on Earth, on Titan, how much would a chunk of ice that weighs 3.5 pounds on Titan weigh on Earth? Well, I can just plug in 3.5. Remember my x and y, where the x was Earth weight and the y was Titan weight. So it's important to keep those assigned and keep those straight so that you don't confuse them, because that would get your whole problem wrong. So if it weighs 3.5 on Titan, I'm going to plug that in for y. And I want to know how much would it weigh on Earth. So x is my weight on Earth. So now I just solve this, right? So times 7 times 7. 3.5 times 7 is 24.5 equals x. So my answer is something that weighs, a chunk of ice that weighs 3.5 pounds on Titan would weigh 24.5 pounds on Earth. So essentially, direct variation is just everything in every linear equation in y equals mx plus b form, but without the b. So you're doing everything the same. It's like you're given x and y points, or if you were given a table of a series of different relationships, x and y's, that you can find the slope. It's just doing what we've been doing in this form. You just don't have a b out here. The b is always 0. So all these direct variations, you can solve for m by plugging in the x, the y, and the x, and then you can find anything you want after you have m, right? You have your equation, and you can plug in any value for y or any value for x to find the other value. So we will do more of this practice in class, but in the meantime, here are a couple practice problems for you. Here are your practice problems tonight. Aren't you excited about it?
Potatoes.
Have fun.